to leave the Earth. NASA relies on the Space Launch System. The Space Launch System, or SLS, is a heavy lift rocket that stands 322 feet tall and generates millions of pounds of thrust. We naturally focus on this massive scale and explosive power when we think of space travel. But the reality of the Artemis II mission is entirely microscopic. 4 human beings will be locked inside the Orion spacecraft. Orion is NASA's deep space crew module, and its livable interior volume is roughly the size of 2 minivans. The crew will live inside this tight space for 10 straight days. This extreme confinement immediately forces us to answer a harsh biological question. How do 4 adults safely manage human waste in an environment with 0 gravity? Inside the capsule, there is a dedicated hinging door built directly into the floor. An astronaut floats over to it, opens the panel, and slides inside a highly specialized, vacuum-assisted compartment to use the bathroom. Millions of pounds of thrust might push a crew out of the atmosphere, but engineering reliable systems for unglamorous, unavoidable bodily functions is what actually keeps them alive in the vacuum. Eating and drinking require identical precision. Without gravity, surface tension dictates how liquids behave. Water forms into floating gelatinous spheres, so the crew must use a specialized device to carefully portion exact amounts of water into sealed drinking bags. This meticulously captured water serves a dual purpose. It hydrates the astronauts, and it is the only way to rehydrate the solid food supplies stowed on board. Sharing a meal involves 4 adults floating in the central cabin space, coordinating their physical movements so they don't bump into each other and accidentally release debris into the air. A single rogue water droplet or drifting food crumb could float into a critical control panel and short out a circuit. Basic sustenance operates as a high-stakes hazard. Once the crew leaves the atmosphere, they face an invisible physiological threat. Without gravity to resist their movements, their muscles rapidly shed mass, and their dense bone matrix dissolves, becoming increasingly brittle by the hour. To counter this rapid degradation, the crew relies on a device called the flywheel. The flywheel is a mechanical tool that uses a spinning disc to generate artificial physical resistance. Mounted firmly to the capsule wall, the flywheel allows astronauts to perform heavy routines. Pulling against varied levels of resistance, they execute high-stress squats, perform heavy deadlifts, and bicep curls to trick their bodies into retaining mass. Even unconsciousness requires mechanical intervention. To sleep safely, the crew must zip themselves into sleeping bags rigidly strapped to the cabin walls, ensuring their resting bodies do not drift into vital life support equipment. In deep space, working out and sleeping are not wellness choices. They are exhausting, mandatory engineering protocols required to prevent the body from shutting down. Once Orion pushes beyond low Earth orbit, the altitude below 1,200 miles where the space station resides, the crew loses the protection of our planet's magnetic field. They are immediately exposed to massive temperature swings and the lethal threat of deep space radiation. To survive a sudden solar flare, Orion features a specialized radiation shelter. It is built deep inside the capsule's core, utilizing dense materials and stowage bags to create a physical barrier against cosmic rays. Throughout the 10-day flight, the crew will run high-stakes emergency procedures. They will test exactly how fast they can barricade themselves inside this core shelter during a simulated radiation event. The data gathered from these specific shelter drills dictates NASA's long-term timeline. If humans are going to survive the multi-month transit to Mars, engineers must know exactly how effective this deep space shielding is in actual practice. Orion operates as an isolated deep space lifeboat. Failing to deploy the radiation shielding fast enough during a real solar storm guarantees immediate lethal exposure. Reaching the target destination requires 4 full days of transit across 230,000 miles of empty space. This diagram shows the mission's ultimate failsafe, the free return trajectory. A free return trajectory is a looping flight path that uses the gravity of a celestial body to pull a spacecraft back to its starting point without requiring engine propulsion. As the capsule approaches the Moon, Lunar gravity catches it and naturally pulls it around the far side. The momentum then slingshots the crew back toward Earth. If Orion's engines completely fail, the laws of physics will still carry the astronauts safely home. This historical chart outlines the Apollo 8 lunar orbital plan. NASA proved this exact gravity-driven survival tactic in the 1960s, and it is the precise orbital mechanic that ultimately saved the Apollo 13 crew after their oxygen tank exploded. But this failsafe also guarantees absolute isolation. Once the rocket fires for the translunar injection, the crew is fully committed. If a catastrophic failure happens midway, they cannot turn around. They must ride the entire gravity wave in the dark. The spatial climax of this trajectory occurs when Orion dips to an altitude of just 4,600 miles above the lunar surface. Crossing over the far side of the Moon, a hemisphere permanently hidden from our planet, the crew loses all visual and radio contact with Earth. They will experience a level of psychological isolation known to only a handful of humans. After the 4-day return trip, the capsule will violently separate from the European service module. The European service module is the uncrewed section, providing power and propulsion. Orion will then slam into the Earth's atmosphere at 25,000 miles per hour before splashing down into the Pacific Ocean. By testing the structural limits of the capsule and the biological limits of its crew, Artemis II proves definitively that the human body and mind can survive the extreme, unforgiving realities of deep space.